Hello everyone, I'm Aryan and thank you all for the support on my last video. And today I've brought some more interesting concepts for you of equivalent springs, which I wanted to tell you something which you might haven't seen before. So I'm going to show you this concept and thank you all for the support. So let's start. So this concept is usually important for SHM and any other spring problem which you may see in NLM or any other chapter. So it's concept of equivalent spring. So what we are trying to do here, basically, first I'll show you a question and then what we're doing to simplify it. So suppose take an example of this question right here. We have a spring connected to a pulley, connected to a spring, connected to a pulley, and then spring, and then a block. And we have to find basically the extension of each and every one of those springs. So suppose this, and how much the block goes down, and the time period of the whole system. So in this is basically a typically lengthy problem where you assume extension x over here, then this would be, since this is connected to the same thing, this would be x, and then this would be x by 2 because the tension is doubled, and then you just write the extensions and then calculate the forces and the standard method. But this concept of equivalent springs will basically absolutely destroy this problem and convert it to this, which we already know what is the time period for this and all, 2 pi root m by k. So, and we'll write k equivalent over there. So it's going to basically destroy this problem into a simple one block problem with a spring. So what we're going to use here is this formula. So what this states is coefficient of t whole square upon k equivalent is equal to sigma of coefficient of t k equivalent. So basically you can look at it as kind of an energy conservation, since t is equal to kx and we write half kx square as energy. We basically are substituting this into t square by 2k, and then we are using this over here. It's not an exact it's just a thing to derive it, so you don't have to remember all that, just remember this. So what this states over here is, I'll show you through a problem only. Since the block is over here, we have to effectively replace a spring over here and remove all of this. So what we're going to do, that is, you're going to write tensions over here first of all. So I think I've written it over here, yeah. So we write, since we have to replace the spring over here, we write tension over here T. This would again be T because it's connected to the same it's the same string. This would be 2T as it's above. This would be T and then T over here again. This T doesn't matter since there is no spring over here. So what we write is, since we have to replace everything over here, we write K effective over here and T effective over here. T effective is just T, and we have to only include the coefficients because the T will get cut anyway. So I've written it over here anyway. So T whole square upon K equivalent is equal to this T over here and 2K, then 2T whole square over K, and then T square over K. So I've written this over here and calculated, and we get K 1 upon K effective is this. Therefore K effective is equal to this. So simply we get the time period by writing 2 pi root of m by k. This is the time period over here. Then first spring, I think, yeah, it was this one. First spring, we write extension as t by k. Therefore the k gets multiplied by k effective. Then this similarly we can write this, and we can find all of the answers, and the answer comes out to be the A, B, and C all. So this question basically gets destroyed into a completely just a problem of one spring and one block. So this is a very important method because it greatly reduces your calculation, and you can just do these type of problems and under a minute. It is very important. We'll take another example over here, and then we'll take another example, and then I'll give you a bonus question, which was very hard to do without this concept of equivalent springs over here, and with it we can do it basically under a minute again. So let's take this problem over here, and the setup of block is shown on the frictionless, so you can read the question. Basically we are pulling this block, and we have to find the extension of this block and how far it will shift. So we write F this, and we write the tension. So I've assumed T in this spring. So this would be t as well, this would be 2t, and this would again be 2t. So since we have to replace the everything on this block, you see that over here there are two tensions, t and then 2t. So you have to write 3 as the coefficient over here, not 2 or not just this, since we have to replace both of them. So this was the important point over here in this illustration. That's why I've picked it. So we write 3 over here, then again we add all these up. So 2 upon k, 2 square upon k, then 1 upon k, and 1 square upon k from all of this over here. And then we write 9 upon k equivalent is equal to 16 upon k, and then we get k equivalent is equal to this. So since kx is equal to f, we for the mean position, we get our answer over here. And we can simply do it under a minute. As you can see, there's no much calculation involved. And then we have another illustration over here, that we are pulling basically this with a force F. We are assuming it with a force F, and we have to find what minimum pull at the end P will bring it to the ground. So again since we have to find the equivalent spring over here, we write t square upon k equivalent is equal to 2t square upon k, and then t square upon k, we get k equivalent as k by 5. And since k effective into x is equal to f, we write f is equal to kx by 5. Simple 2-line solution. You have to do nothing over here. Another problem, I think this is the last one, and then I'll give you a bonus question. We have 2 springs over here connected to a pulley, and then again connected to a pulley, and we have to find how far does a block descend during the process of reduction of force. Once again, let me read the question. Force supporting is the block is okay, so we are holding this block with the force F, and we are gradually decreasing this force, and we have to find out again the same problem. We have to find out the extension. Same, we are going to do kx is equal to f, and then since there is mg acting on this, that is equal to mg. So how do we find k effective? Since assuming t over here, so t 2t, then 2t again, and then 4t. And so basically another point I would like to add, assume t in always the lowest this thing, because adding fractions is annoying, right? Just a little, nothing is going to happen. It will take less than a minute only, but just to make calculations easier. So that's why I've assumed t in the lowest point, and then it only increases by multiples above. So 4t over here, so we write 4 square upon k equivalent is equal to, and this tension doesn't matter, right? 2t over here, there's no spring over here. This matters and only this matters. So t square upon k, and 2t whole square upon 2k. So again we get k equivalent as 16k upon 3. Then we again write kx is equal to f. In this case, f is equal to mg, because we are reducing the force. We have put our hand over here initially, and then we are gradually reducing the force, so only mg will be acting on it. So if there was a force applied by it, let's say some 2 mg, so we have to write the normal force which we have applied minus mg is equal to kx. So, but over this is equal to 0, so only mg, and then x is equal to mg by k effective, and then we get simply this is the answer. So this basically reduces the problem to a simple one block system, which is and everything we know about that already, that the mean portion is mg by k, it oscillates, the time period, everything we know. And now again I'm going to take up a problem here, which was again given by the Indian School of Physics. It's a good question, and I think it would be incredibly hard to do without the calculations of effective spring. So let me just take that problem once again. So this is the problem right here, and it's a system of infinite pulleys where in a geometric progression with spring constant. So this would be k1, k2, which is k, once again, k, then k by 2, k by 4, k by 8, and so on till infinity. And there's a block over here, and we have to find the time period of the system. So again we'll use this concept, and since we'll have to just assume a tension t over here, so all the springs over here will have 2t only. As you can see, since this wire will have tension t, and then above this 2t, 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 and 2t, and all of these there will be 2t only. So again we write 2t the whole square upon, suppose one was k, then it starts with k only, right? Okay, acha, it's in multiples, okay, no problem. So 2t the whole square upon 2k, then 2t the whole square upon 4k, so on till infinity, is equal to t square upon k effective. Since the t, we have to replace everything over here, so we'll use t over here only. So now we just take 4t square as common, and t square gets cut, times 1 and k also. You get 1 plus 1 by 2 plus 1 by 4 till infinity is equal to 1 upon k effective. So this sum is again 1 upon 1 minus 1 by 2, that's 2. So we get k effective as k by 8. And then we can just write the time period of the system as t is equal to 2 pi root m by k effective, which would be k by 8. So this matches with their answer, and simply we have again converted into a simple one block system. So this was the new concept over here which I wanted to tell you, and it is very useful. I've used this in many other questions also which I have not shown over here, and you can too, and it's very easy to remember too. So thank you everyone for the support on the last video, and I think this would be probably my last video till after my boards, because I have to do PE. So thank you everyone, and thanks for watching. Bye.